Swayam Prabha. Digital India. Educated India.
Hello and a very warm welcome to all of you to this course on gas turbines and jet engines. So, today is lecture 10 of the course, which is the final lecture of week 2, and today we are going to learn we are going to perform analysis of intercooled Brayton cycle. We have started discussing intercooled Brayton cycle in the previous lecture or in the previous class. We will continue from there and we will try to derive an optimum condition where we get the best or most optimum intercooling, which means that lowest work input is needed for the compressor. So, the concepts that will be covered, one is optimum intercooled cycle. So, how to derive the optimum condition at which we get the minimum intercooler work input, which means that we get the maximum work output from the cycle. Okay. And the second point is comparison of performance characteristics. So, variation of efficiency and non-dimensional net specific work output for intercooled cycle with the corresponding variations for the previous cycle that we have studied. We will see how it compares with the previous cases. Okay. So, let us quickly revisit once what we mean by intercooling or what we mean by intercooled cycle. I will draw on the right hand side. So, let us start afresh. So, let us say that. So, I will draw the TS diagram. You can refer to the previous class notes also or previous class discussion. So, now we have two compressors, if you remember, one the low pressure compression going from 1 to 2, then constant pressure heat removal, and then from constant pressure heat removal 2 to 3, which we called as the intercooling process. Okay. And then from 3 to 4 is the high pressure compression. Then from 4 to 5 is the heat addition. Okay, we will draw it in a better way. Four to 5 is the constant pressure heat addition. Then we have expansion in the turbine 5 to 6. So, this is 4 to 5 and then expansion in the turbine 5 to 6. And then we close out the cycle by adding a hypothetical heat removal process 6 to 1. Okay. This we had discussed and we have derived some expressions. So, in terms of performance parameters, so we had defined parameters, we already know R and C and T, but we also defined RA and RB and CA and CV. Okay. And we know that R should be equal to RA into RB, that also we have seen in the previous class, and C is equal to CA into CV. Okay. So, they are not independent, they are related. So, net work output, we had obtained an expression net work output divided by CPT1. So, non-dimensional net work output equal to T minus T by C, okay, minus C A plus 1 minus C B plus 1. So, this was derived by using the expression of W net, which is the work output from the turbine minus work input to both the compressors. Okay. Now, to get the optimum value, of the intercooling process or optimum condition for intercooling, we will take a derivative of this. So, d d C A of W net by C P T 1 with respect to C A or C B, anything is okay, because both C A and C B are related. So, if we take with respect to C A, automatically the effect of C B is also incorporated into the calculation. Okay. So, now what is this value? So, we find that this is equal to, so this first term gets cancelled 0 minus T by C, this also becomes equal to 0, okay, minus C A. So, this will become equal to minus 1 plus 0 minus C B. So, what is minus C B? Minus C B is minus C by C A. Okay. So, minus C by C A. So, derivative of that is plus C by C A square. Okay. And then final term is 0. So, this is equal to 0, which means that C is equal to C A square, okay, from these two terms, non-zero terms, or this means that C A is equal to C B is equal to root C. Okay. So, again similar to reheat cycle, we see that here also if the pressure ratios are equally divided, okay, both the compressors have same pressure ratio, then we get the highest work output from the cycle. This is a condition which is in principle similar to that we had obtained for reheating, where also we found that if the pressure ratio of expansion in the turbine was equally divided between the two turbines, we obtain the highest work output. Okay. So, similarly we get a same type of condition here. So, this means that R A is equal to R B is equal to root R, okay. And because C A is equal to, what is the meaning of C A? So, C A is R A to the power gamma minus 1 by gamma. So, this is equal to T 2 by T 1, and C B is R B to the power gamma minus 1 by gamma, this is T 4 by T 3. This means that, let us write here. So, if C A is equal to C B, we know that T 2 by T 1 is equal to T 4 by T 3. Now, we have assumed that T 1 and T 3 are equal, which will be the case for normal applications, because we cannot go to a temperature below the ambient temperature. Okay. So, if I want to go to a temperature in the intercooler to a temperature below the ambient temperature, we will need a coolant which comes at lower temperature compared to the ambient. So, which means that that itself has to be refrigerated. So, the entire purpose of increasing the work output is lost in that case. So, the limiting value for a practical situation is the ambient temperature itself. Okay. So, if it means that T 2 is equal to T 4. So, we get the most optimum condition or the maximum work output when this T 2 is equal to T 4. Okay. T 2 is equal to T 4. This gives us the maximum work output, and of course, T 3 equal to T 1. So, the work input to both the compressors are same in this case. Okay. So, this is how we should divide the pressure ratio. Now, we want to find out, okay, so this is the optimum condition. So, what is the efficiency at the optimum condition? We want to find out what is the efficiency at the optimum condition. Okay. So, efficiency at the optimum condition, we will go with the basic definition. Efficiency is W net by Q in. Okay, in our case W net is Cp T1, then T minus T by C minus Ca plus 1 minus Cb plus 1. Okay, this is W net divided by Q in. Q in is Cp into. So, let us take a look quickly. T5 minus T4. Okay. Cp T5 minus T4. So, if I cancel Cp T1 from both the numerator and the denominator, we are left with T minus T by C minus Ca plus 1 minus Cb plus 1 divided by T5 by T1 minus T4 by T1. What is T5 by T1? T5 by T1, okay, T5 by T1, we can see that this is equal to T. And what is T4 by T1? T4 by T1 is equal to T4 by T3. This is equal to Cb, okay, Cb or Rb to the power gamma minus 1 by gamma. So, now we have T minus T by C minus Ca minus Cb plus 2 by T minus Cb. Okay. Now, remember that for optimum condition, Ca equal to Cb equal to root C, right. So, which means that efficiency for optimum condition is equal to T minus T by C minus 2 root C plus 2. It is a complex expression. Remember that, again I will emphasize, this is not a formula. So, we should not use this as a formula. This is an expression that we derive, so that we can understand the performance characteristic, plot the performance characteristics, performance maps, how efficiency varies with T and R. Okay. That is the purpose of this derivation, and to find what are the optimum conditions. So, this divided by T minus root C. Okay. So, eta is equal to T minus T by C minus 2 root C plus 2 divided by T minus root C. So, this is the maximum efficiency. This is a complex expression, means complicated expression. Directly we cannot say how the efficiency varies with T or C. So, we need to plot using some numerical tool the efficiency for various values of T and C, and from there we should be able to find how the efficiency varies with T and C, okay, for this optimum condition. So, from now onward, unless otherwise mentioned, we will assume that the analysis for intercooled cycle is always done at optimum condition for the intercooler. Okay. So, now let us try to compare the performance characteristics for this optimum intercooled cycle with all the previous cycles. Okay. We will try to understand how the performance characteristics vary in this for this case and how it is different from the other cases. Okay. Let us first draw the efficiency versus work versus R pressure ratio, and we will also draw the net specific work output in non-dimensional form W net by CPT 1 and this is R, okay, versus R. So, we know that for standard Brayton cycle, okay, we will use the red color itself. So, minimum is R equal to 1, there the meaning of cycle does not exist if R is less than 1, R less than 1 cannot exist. So, this is the standard Brayton cycle, a simple Brayton cycle. Then we will compare this intercooling with reheating. Okay. So, for reheating we had efficiencies like this. Let us draw it with some separation. Okay, so, this is for say t equal to 3, t equal to 4, t equal to 5 for reheat. So, we need not draw the regeneration and reheat plus regeneration, because the behavior in those cases is very different. So, here it is more apt to compare with the reheat cycle, because ultimately our aim is to increase the work output. We will see what is the resultant effect on the efficiency. Okay. So, for the intercooling we will use another color, let us say that we will use green. The efficiencies are less affected as compared to reheating. This is also something which you should think of, why the effect of intercooling is less as compared to reheating. So, important question. So, although the efficiency decreases, so here also the efficiency decreases, but the decrease is not as drastic as the reheat cycle. Okay. It decreases by a lower extent. So, the efficiency is higher compared to the corresponding reheat cycle. So, here for example, this line will be t equal to 5, then we will have this bottom line is t equal to 3 and in between we have t equal to 4. So, if we compare the corresponding lines, so for t equal to 3 intercooling will have higher efficiency compared to reheating, t equal to 4 same case, t equal to 5 also same case. But again similar to reheat cycle, for intercooled cycle also the efficiency is lower than the simple Brayton cycle. It will never reach the simple Brayton cycle efficiency, but it keeps on increasing with increasing t, and it then generally it keeps on increasing at a lower rate. So, ultimately you can never reach the efficiency of the simple Brayton cycle. So, we see that in terms of efficiency there is a drawback of this cycle, but that we expected, because our main purpose was to increase the work output. Okay. So, in terms of work output, if the standard Brayton cycle work output is like this, again I will use red color for the standard. So, we will use some standard colors. Let us say that this is t equal to 3, t equal to 4 and t equal to 5, okay. T equal to 3, t equal to 4, t equal to 5. Remember that for standard cycle also the effect of t is present when we consider the net work output. Okay. So, this is standard. So, with increasing T we know that the work output will increase. All of you should know what is the reason. With increasing T the turbine inlet temperature is higher. So, we get higher scope for work output from the turbine. Okay. Now, coming back to this. So, for reheat we had seen that there will be considerable increase in the work output. So, for example, qualitatively it can be something like this, T equal to 2 for reheat, then T equal to 3, sorry, let us say that this is T equal to 3, this will be T equal to 4, T equal to 2 we have not drawn because that has very low values and is not practical in modern times. Okay. Then this is T equal to 5. So, considerable increase in the value of the net work output occurs, and we have seen what is the increase. Typically, it can be 20 to 25% for realistic values of the say design parameters. Okay. So, this is for reheating. So, the effect of intercooling is not as much as reheating, but still it increases the work output compared to the standard cycle. So, if I draw the intercooled cycle work variation, net work output variation, it will be somewhere in between the corresponding case for reheating and for the standard case. So, this will be T equal to 3 intercooled, or intercooling. Then so we should compare these three, right, this T equal to 3, T equal to 3 and T equal to 3. Similarly, for T equal to 4 we should be in between these two. Okay, there is no crossover here. So, T equal to 4, again we should compare these and these. Okay. And similarly, for T equal to 5 we get a slightly lower value as compared to the reheat cycle, but significantly higher value compared to the standard cycle. Okay. So, intercooling has similar advantages to reheating, but the quantitatively the amount of increase of work output is lower as compared to reheating. On the other hand, the efficiency decreases similar to reheating, but again quantitatively the effect on efficiency is less drastic. So, efficiency does not decrease as much as the reheat cycle. Okay. So, this pattern will continue. So, if you compare these three should be compared, we will continue for higher T. So, with T increasing T, the work output increases, the efficiency also increases with increasing T, but in one case this is less than the simple Brayton efficiency, but the work output is greater. Okay. Now, if we come back and revisit the question, why the effect of reheating is more, okay, quantitatively, say reheating has more drastic effect on both the improvement of work output and the decrease or drawback or decrease of efficiency. So, if we go back to the cycle, okay, or if I just compare say side by side, let us say so the intercooling occurs. So, if I have two constant pressure lines, okay, for ideal gas, we know that the constant pressure lines diverge. Okay, let us say that this is P 6 and this is P 5, like what we have seen in our intercooling case. Now, any changes which is made in this region at lower temperature will mean that the effect is lower as compared to any changes corresponding similar changes made in this high temperature region, because here any changes will lead to more significant changes as compared to this. So, for example, if the work output changes, the work output change or work input change here will be much higher, or which will have a much lower, which will have a lower effect on the overall work output as compared to any work transfer change which occurs here, because here the distance between the constant pressure lines is high. So, the effect of reheating which occurs at high temperature is more drastic as compared to the effect of intercooling. Okay. So, to summarize, this intercooling is a process, conceptually it is similar to reheating, but practically it is a difficult process in the sense that you need a bulky intercooler, but bulky heat exchanger, and you need external source of water, and this water needs to be supplied continuously for cooling. So, it removes the self independence of the gas turbine cycle, unlike say reheating, where we can inject fuel, because very small amount of fuel is needed, we can keep on injecting fuel in the for secondary combustion. Okay. The effect, however, for this can still be used, and this is used for industrial gas turbines which are installed at a fixed location. So, there is no necessity of moving this. So, the weight is of less consideration, and supply of water is also abundantly available in locations of power plants. Okay. So, in those cases we can get significantly higher net work output, which reduces the overall size of the plant, because it reduces the mass flow rate of the working fluid, and the penalty to the efficiency is not as severe as compared to the reheating. Okay. In the next classes we will see that intercooling, when combined with regeneration, has a very strong positive effect. So, intercooling is very powerful when it is combined with regeneration. So, nowadays if intercooling is used, it is used only in combination with regeneration. Okay. So, with this we will conclude today's class. So, today we have derived a condition for optimum intercooling. We have found what is the efficiency of a intercooled cycle at that optimum condition. Then we have seen how the variation, or what is the variation of efficiency and non-dimensional net specific work output, which together comprises this performance characteristics. So, we have seen how these vary with design parameters R and T for intercooled Brayton cycle, and we have compared them with similar cycles. So, the reheat cycle and the simple Brayton cycle, and seen that the effects are the effects are similar to the reheat cycle, but less drastic. Okay. So, these are the references, and with this I finish today's class. So, we will meet again in the next class. Thank you.